All right, I'm on page 19. This is the answer key to the circular motion problems. Okay. So number 27, the clothes in a railway dryer whose radius is 0.25 meters are moving with a tangential speed of 2.3 meters per second. What's the centripetal acceleration? So the centripetal acceleration is v squared over r. So you have your v, you have your r, and all you have to do is divide. You should get an answer of 21.16. The next one, we give it an acceleration. That's your centripetal acceleration. And we're trying to find the speed, okay, at a radius of 6.5 meters. Again, these are extremely simple. So you just plug in basically, plug and chug. So AC is equal to v squared over r, and I'm sure you can figure out the speed is there. Okay, a car will skid if the acceleration as it makes the turn is more than 3.5 meters per second square. If the car is traveling at 20 meters per second, what's the radius? Same idea. Write this formula here, put 3.5 here, 20 square over r, and you should be able to solve that equation. Okay. I'm going to go through this pretty quickly. A child having a mass of 30 kilograms sits 4 meters from the center of a merry-go-round that is rotating with a period of 10 seconds. What's the speed? What's the velocity? So velocity is circumference over period. And that should be just 2 pi times 4 divided by over 10. And you get your velocity to be 2.51 meters per second. Second part is what's the net centripetal force. Okay, again, centripetal force is not a force. It's just like the net force in Newton's second law. That's going to be mv squared over r. So the mass is 30. The v, you just found it. You square that and you divide it by 4, and that's that. A model airplane of mass 2 kilograms is observed flying at a constant speed in a circle whose radius is 5 meters. The time for each revolution is 4 seconds. Find the net centripetal force. So the net centripetal force is mv squared over r. Okay, so the mass is 2. Now to find the v, you would do, I guess, 2 pi r, which is 5, over the period, which is 4, and you would square that divided by the radius. Okay, and you should get 24.67 newtons. All right, let's look at 32. Okay, a 0.013 kilogram stopper is attached to a 0.93 meters length of string. The stopper is swung in a horizontal circle, making 1 revolution in 1.18 seconds. Now, it's extremely hard to do a horizontal circle because the weight of the object will force the mass to drop a little bit, right? So it depends on how fast you're going. So it's almost going to look like a cone instead of a circle. And we'll do this in a lab. Find the stopper speed, centripetal acceleration, and the net centripetal force. So if we want to find the speed, that's 2 pi r over period. So 2 pi r, which is 0.93, over the period, which is 1.18. And you can do the math there. Centripetal acceleration is just v squared, whatever you get here, divided by r, which is 0.93. And the net centripetal force is whatever acceleration you get. You don't have to do mv squared over r because you already found the acceleration. You just take the mass, must be in kilograms. So in other words, if this were given in grams, you'll have to change it and times the acceleration to get your force. All right, next page. Okay. A racetrack designed for an average speed of 240 240 kilometers per hour. So that has to be changed right away to meters per second. So let me see my notes here. So that's 66 and 2/3 meters per second. Okay. Is to have a turn with a radius of 975. To what angle must the track be banked so that the car traveling at that speed have no tendency to slip sideways? Now we're going to do this. You can actually make a turn here without relying on friction, period. So this is the car, and you're going around this way, right? Around the racetrack. So here is your mg. Here is the normal force. Okay. Now the center of this here, car is going this way. The center of this curvature is somewhere in here. Okay. So I'm going to break this, and if this angle here is theta, right? This is also theta. We proved this a long time ago with the inclined planes. So these are the components of the normal force, which we'll erase later. Okay. Now, if you go back to the previous video, you're going to see that I showed you a proof that shows that tangent of this angle here of the bank is equal to v square over gr. Okay. So basically, what's responsible for the turn is the horizontal component of the normal force. Okay, it's pushing you kind of like in. So if we do the math here, we have the V, which is 66.67. We have the G, which is 10. We have the radius, which is 975. And you can just do an inverse tangent, and you should get an angle of 24.51. So you don't have to show the proof all the time. If you can just memorize that, that's not in your formula sheet. If you can remember that, but you still, and you can use it, but you still have to draw a free body diagram, which really is not hard to do. Okay. For the next question, you're doing the same thing. Instead of finding the angle, you find in the speed. So basically, it's going to be tangent. After you write the formula, 68 is v squared over g r. Okay, and you can figure that out. That's not too hard to find. Okay, number 35. Okay. A ball on the end of a string is revolved at a uniform rate in a vertical circle. So now instead of going horizontally like this, you're going vertically, right? So it's like this basically. So here's my tennis ball. So whenever it says a vertical circle, you're going like this. When it says horizontal circus, you're going like this. Okay. Okay. If the speed is 4.15 meters at the top and 7.17 meters per second at the bottom, and the mass is that much, calculate the tension when the ball is at the top and at the bottom. Now, at the top, you have F centripetal net is mv squared over r. Okay. You have mg plus the tension at the top. I guess I can call it tension 1 equals mv squared over r. Okay. Now to find the tension, you're just going to be mv squared over r minus mg. Now you have the mass, you have the v at the top, you have the radius. You have to change that radius to meters. So instead of 85 centimeters, you have to write 0.85, and you can just find your tension, and that's 3.08 newtons, right? At the bottom, it's a different story. Now we're going to we're going to choose towards the center as positive all the time. So it's going to be tension at the bottom, which is tension 2, minus mg is mv squared over r. And you do the same thing, and you get 21.08. Okay. Okay. Now let's look at this ranking or this problems where we have to explain. A ball with a mass of 2 newtons, so the Fg or the mg is 2 newtons. okay, is attached to the end of a cord of length 2 meters. The ball is, so the radius is 2 meters. The ball is whirled in a vertical circle counterclockwise. The tension in the cord at the top is, so you're going to have 7 newtons in this rope here, and at the bottom you're going to have 15 newtons. And at the bottom it's always going to be higher than the top, and we talked about that previously. 3 students are discuss the net force on the ball at the top. Okay. All right. So let's see. Angelica, the net force on the ball at the top position is 7 newtons, since the net force is the same as the tension. That's not true. At the top, the net force is the mg, which is 2 newtons, and the 7 newtons. So that's out. The net force on the ball at the top position is 9 newtons. That's true. Both the tension and the weight are acting downwards, so you have to add them. That's true. Charles says, no, you are both wrong. You need to figure out the centripetal force, mv squared over r, and include it in the net force. Well, we can't do that. Okay. All right, the next question. Now the students discuss the net force at the bottom. Well, at the bottom, the net force on the ball at the bottom is 15 newtons. That's not true. The net force at the bottom is 17 newtons. I don't think that's true either. Okay. The net force on the ball at the bottom is 13 newtons. I don't think that's at the bottom. Let me see. Oh, hold on a second. Yes. Okay. So let's see. Oh yeah, at the bottom the tension here is 15, and the mg is 2. So the force at the bottom, or the net force at the bottom, should be 13. So let's see who's got it right. It looks like Charles got it right. So let's make sure his statement is completely right. The completely correct. Net force on the ball at the bottom is 13. I agree that you need to take into account both the weight and the tension, but they are in different directions, so they will subtract. That's true. Okay, now 36. How much must the static coefficient of friction between the road and the tires in a car, if a car is to make a level curve, let's say level, this is not banked, okay? This is flat. So I'm going to try to draw it. So going around the curve, okay? And this is the center of the curve. So this is the car is here. So this is the static friction that's allowing you to make the turn. Okay. You also have your mg and your fn have to be equal. So that's your free body diagram. And this ff is perpendicular to mg, which is in the same direction as fn. So you have to look at that in 3D. All right, so the centripetal force, the net centripetal force, is mv squared over r. Now here they are not giving us the mass of the car, so hopefully the mass will cancel out somewhere. Now ff is mu static times fn. And fn is the same as mg. And that's mv squared over r. And you cross out the m's, and mu static is v squared over gr. Do not memorize this, you have to show it. And if you do the math, you'll get, let me see, you get 0.82 and no units. And make sure you change this 95 kilometers per hour to meters per second, which comes out to be 26.89, 0.39. All right. Okay. At what minimum speed must a roller coaster be traveling when upside down at the top of the circle if the passengers are not to fall out? So this is how we're going to treat this. We're going to do it, and we're going to figure out with what speed the passengers will fall. And then we just have to say we just have to be going at a speed greater than that number. So here you have the normal force, the track is pushing back on the people, right? And then you have your mg. Now your centripetal force equals ma. That must be equal to the mg plus the normal force equals mv squared over r. Now we're going to say, you know what? If they lose contact with the tracks, then Fn is 0. There's no more contact. Now we can find the v, and that's going to be square root of gr in this case. So that's the square root of 10 times 8.6. So it's got to be 9 and change, right? So which means the v at that speed, they're falling off. So they have to be going faster than that. Okay. Okay. 1,000 kilogram sports car moving at 20 meters per second crosses around the top of a hill. So it's kind of like this. So the car is here. Okay. Determine the normal force on the car, the normal force on the 70 kilogram driver, and the car's speed at which the normal force equals 0. In other words, for part C, the tires no longer make contact with the road. Here you cannot say that Fg is equal to Fn. And the reason for that, because this is not a flat surface, so you have to be extremely careful with that. All right, determine the normal force on the car. Well, Fn. So Fn is this way. The mg is down this way. So, and the curvature of this arc here, or this hill, is maybe somewhere down there. So I'm going to do mg minus Fn is mv squared over r. So which makes Fn equal mg minus mv squared over r. Now mg is 10 times 1,000, so that's 10,000 minus 1,000 times 20 squared over the radius, which is 100. And if you do the math here, you should get, let me see, 6,420. Okay. The normal force on the car, the normal force on a 70 kilogram driver. You do the same exact thing as in part A, except now instead of using the mass of the whole car, you just concentrate on the driver. Okay? And the speed at which the normal force equals 0. In other words, how fast you have to be going so that you lose contact with the tracks. So all you have to do here is just come in here and make Fn 0, and you end up with mg equals mv squared over r. We don't even need the mass. So v is square root of gr, and the r is given. So it's a square root of 1,000. So if you go in at 31.62 meters per second, you lose contact with the tracks. Okay. Now the next one is, how fast can Katie drive in her BMW Z4 without skidding if the radius of the chair is 30 meters and the coefficient of static friction, see how I say static friction here? It's not kinetic. Between the tires and the road is 0.75. All right, same thing. So you're going to draw your free body diagram. Okay, so this is your centripetal force. That's what plays the role of centripetal force. Going up is your normal force, and down is your mg. And those two are equal because the car never leaves the surface. So I think I can say the F static equals mv squared over r. Ff static is mu Fn, and Fn is the same as mg. So this is mu mg, and this is mu static, of course, is mv squared over r. And whenever you are not given the mass, it has to cross out somewhere. Okay, so which means really the mass of the car here doesn't matter. It could be a truck, it could be a car, it doesn't matter. So, okay, so v is square root of g times r times mu static. And you can figure that out. And your answer should be about 15 meters per second. All right, last page. Okay. Number 40 is a little bit challenging, and you're gonna see why, because this is a cone. This is not a flat. It's not a horizontal circle. All right. So the first thing you want to start with is, do the forces acting on the object? So you got your mg here, and you have tension in this cable here. Okay. Now, the center of this circle is somewhere in here, right? You have to look at, I see this in 3D. It's just like the pig hanging over here. All right. Okay, so this length here is 15 meters. Now, this 15 meters, that's not the radius of the circle. The radius of the circle is here. That's one of the common mistakes. People think that's the 15 is the radius of the circle. Okay, determine the tension in the cable. And I think we know how fast we don't know how fast we're going. Okay, so to find the tension, I'm going to write my statements in the x and the y direction. Now I'm going to draw the components of T, and then I'll erase them later. So T has an x component going to the left and a y component going up. And this angle here that I'm marking, that's 60 degrees, because those are corresponding angles. So you can see that. Okay, you got two parallel lines in here. So if I want to find this tension here, I think I can say that the tension, the y component of tension, is equal to mg. Okay, because that motorcycle stays at the same level. Okay, so Ty, and I hope you can see this, the Ty is just T cosine of 60 degrees, right? The Ty is the adjacent with respect to that angle. Now, if you want to work with 30, you can, but it doesn't make a difference. So T is basically mg over cosine of 60, which is 179 times 10 divided by cosine of 60, and that should give us a tension of 3,580 newtons. Okay. Now, to find the speed, if the only question that we would ask is to find the speed, we actually don't need the mass. Right. So to find the speed, it looks like Tx is what plays the role of your centripetal force. Right. So Tx is basically T sine of 60. Okay. And so we already found the T. We have everything else we need, so I think you can find the V. Let's just say part A was not asked, and we just have to find the speed of the chair, and they don't tell us what the mass is. So this is what we have to write. We have to write two equations. We have to say, you know what, T cosine 60 is mg, and we say T sine of 60 is mv squared over r. And I think if you divide in this direction, I want to end up with a tangent. I can get rid of the T and the m at the same time. So I end up with tangent of 60 is v squared over gr, right? Okay. Okay. Now, you're on a circular bump. Okay, so is the normal force exerted on the skateboarder by the ramp, by the bump, greater than, less than, or equal to the weight of the skateboarder? Well, when they're up here, this is your mg, this is the Fn. Okay, so the normal force is acting up, and the center is down here. So my centripetal force equals mv squared over r should be mg minus Fn is mv squared over r. So which makes Fn equals mg minus mv squared over r. And you can see clearly that this is less than mg. Now your Fn is less than mg. Now, the last one, okay, so let's look at who is wrong here. Aliyah, at the bottom of the swing, she will be moving exactly horizontally. Since she's not moving vertically at that instant, the vertical forces cancel. The tension in the rope equals the weight. That's not true, because even though she's at the bottom, the velocity is still changing. She might be going at a constant speed, but the velocity is changing. Brian, just look at the velocity vectors. The change in velocity points upward between A and B. So that is the direction of the direction of the acceleration and also the net force. To get a net force pointing upward, the tension would have to be greater than the weight. That's true. Okay? And here is why. And you can look at my notes. See, the final velocity is 2 meters per second here, this one. Then the other one you have to subtract. So this is the other 2 meters per second, or negative basically. So which means the difference is acting up, right? And the change in velocity has the same direction as the acceleration, which has the same direction as the net force, the net centripetal force. So Brian is correct. All right, I'm out. Peace.